nice to be here. I'm going to be presenting today on HBase Global Indexing to support large-scale data ingestion at Uber. And before I get started, just let me introduce myself. First of all, it's a real privilege to be here. So my name is Danny Chen. I'm currently an engineering manager on the Hadoop Data Platform team. Before I transitioned to a management role, I was an IC on the team and was a co-creator of the Marmory ingestion and dispersal framework that we'll also talk about today in context with how we actually support HBase Global Indexing. And previous to Uber, I worked at Twitter on the storage team. I was one part of the core team that created this key value store called Manhattan. So I actually have, I'm not sure if you guys, it's semantically similar to Cassandra. So I have a particular affinity towards data stores and NoSQL, so it's really great to be here. Just in terms of like some personal pursuits that I like to do in my free time, I love playing basketball, I enjoy biking, and I got two little kids I love to spend time with. So first of all, our team mission, I'm just going to read this straight out to you guys so you guys know what the purpose of our team is. So we want to build products to support reliable, scalable, easy to use, compliant, and efficient data transfer, both ingestion and dispersal, as well as data storage leveraging the Apache Hadoop ecosystem. So the overview of our talk today, first of all, I'm going to give a high-level introduction to our Hadoop Marmory ingestion and dispersal framework. And then I'm going to talk about the different types of workloads that we see in our ingestion systems. Then that's going to be followed up by why there was a need for a global index, specifically using HBase, how the global index actually works, both with how we generate it and how we actually use it in production. Then we're going to talk about how we generate the global indexes with H files. And then I'm going to talk about a little bit about how we actually throttle HBase access, and then we'll talk about next steps. So to give a high-level ingestion and dispersal introduction, so this is our Hadoop data ecosystem at Uber. If you see, the whole point, the dispersal framework and ingestion framework is called Marmory, and we really thought of it as ingestion and dispersal of data is not really different. It's really just moving data from one place to another where it maximizes the effectiveness of that data. So if you look at this diagram, the way that we built it was that it was agnostic to any source and any sink. So what we can do is we can actually ingest Cassandra, MySQL, Kafka, and there is a Uber schema list that's a proprietary data store at Uber that is ingested into our Hadoop Data Lake through our Marmory ingestion framework. You run analytical processing on top of that. So for example, Michelangelo is our machine learning platform. You can run things such as you can run Uber Eats recommendations is something that is very popular on our platform. And then once you have that, you have these derived data sets of immense data value that is stored in Hadoop. Obviously, if you try to access that data, it can take on the order of minutes to get that in Hive, even hours potentially. And so you can't wait for these recommendations when you open, for your Uber ride or your Uber Eats app. And so we disperse it into low latency data stores such as Cassandra using Marmory again dispersal. And then when now you have like sub 10 millisecond latencies usually for reads on Cassandra. So this is an overview of our Hadoop data ecosystem. The global indexing is built into this. This was open source last year. And we actually have a talk tomorrow about this as well. So feel free to come tomorrow at 11. Just a different quick look at how this actually works. So we have our data producers. They encode their all the data using Avro, and it's written into our ingestion service, and we store it in Hadoop in something called Hoodie, which is another open source project at Uber. So as you guys know, that data in Hadoop is usually immutable, and Hoodie is an abstraction that is built on top of Parquet files. It's metadata that encompasses it. And basically, it gives you the abstraction of updating and deleting your data. So it basically gives snapshot isolation, so the readers don't block writers and the writers don't block the readers. And from that perspective, you can actually see the latest updates, even though the old data still exists. So you can run queries in real time. It'll never affect any of our latencies for writes or reads. And so that's basically how it works. We have a schema service layer on top of it. So all our data in Uber is schematized to ensure that there's high data quality in our data stores. And then analytical data users can go directly to our data lake to run queries, create new derived data sets, et cetera. And then, of course, we have the dispersal service as well. So now I wanted to talk about the different types of workloads. So I'm going to focus mostly on ingestion during this talk. And so there's two types of workloads. The first one is called Bootstrap. So Bootstrap occurs only at the beginning of the lifecycle. So I'm going to use trips as an example for most of this talk. So, trips from Uber, Uber Eats, jump bikes, scooter rides, everything that we do is modeled as a trip in our table. And so if you think about it, when we first onboard this table for ingestion, there is a huge, over 10 billion rides that we have to onboard and bootstrap into the Hive table before we can start querying it. And so this is all the historical data that's in Hive, and this is a large amount of data. And in order to actually do this in a performant manner, we have to complete this in a matter of hours. The reason why is because once you start the bootstrapping process, we still maintain the incremental changes in Kafka or some other sort of distributed log so that we can't fall too far behind before we start the incremental process to catch up. Otherwise, we're going to have a lot of problems with latency and freshness of data, and a lot of the data scientists and analysts will start complaining. And so from that perspective, if you think about ingesting all this data in a matter of hours, it's actually, the QPS throughput is actually in the millions. Now, if you think about it from a NoSQL store perspective, there's no NoSQL store that can really handle millions of writes per second, right? And so that's our first example. And the second one is incremental. So now incremental dominates the life cycle of our Hive table ingestion process. So once you've bootstrapped this data and you've caught up and you have all the data in Hive for analytics, all the new changes that come in, you need to incrementally update these tables. Now, the QPS is in the thousands for this data set, and that is something that NoSQL stores can definitely handle. And so that is the second part, and we'll talk about next is the cell versus a row. So now you have the bootstrap and the incremental that gets all your data into Hive. Now, in the data in Hive, we have internally at Uber what we call cell tables and row tables. Now, if you look at it from a trips perspective, a cell table is all the incremental changes in the history of a trip, while a row is a snapshot of the latest data of the trip. So, for example, if you call an Uber and you're going to destination X, and during the ride, and we give you an upfront price for it, right? And during the ride, you say, actually, we need to go somewhere different, and you update your endpoint. And so your trip price will update now. Now, let's say you finish your trip, and then you forgot that you had a coupon to apply. So you applied that coupon, and now your trip price changes again, and then you realize your driver was really nice, and so you tip them, and you add more after the trip, and then you add additional change to additional price to the trip. So all these changes are actually captured in what we call the cell change log, so you can see the history of a trip. In the row table, every time that you update the price, we need to update the row table for the latest value of the trip. So we don't have all those historical changes. So we maintain these two separate tables. So if you look at this slide here, we just have, this is just a generic example, but we have a row key. If you look, we input these change logs, and if you look on the top right, we have row 1, column A is value A at first, and then later it's updated to value D. Column B is first, the value is B, and then it is updated later to C. Now, that is the changelog table at the top right. At the bottom right, that is what we call the row table, the merge snapshot view, and that is our row table. So in that point, we'll actually update, we'll update in the row, so when people read it, they only get the latest values, right? And so that's part where Hoodie comes in, where we actually are able to overwrite the Parquet files with, we don't overwrite, we create a new Parquet file with the latest data, and then there's a compaction process on the back end that will deprecate the old Parquet files. So the need for the global index. So where this comes in is basically, again, we have large amounts of historical data that is ingested in a short amount of time. We really need this for the append plus update use case. So that is the row table that I talked about first. So if you take a look at the previous example I was just discussing, the cell table once that change is there, it's immutable. It's never going to be changed again, even if it was a mistake. Like the trip price was a mistake, you create it, then you have the history for the next trip price, the corrected trip price. But the row table, that has to be updated every time. And so we need to be able to do that append plus update use case. We need to be able to handle that in a way that, that is performant. We also have to think about the data layout and the partitioning. So at Uber, currently everything that we, in our Hive tables is date partition. So we partition every single day has all the data for all the trips for that day. And so we need to think about, with the global index, how do you avoid full table scans whenever it's possible? And how are you able to write to the correct partition in the most performant way possible? So when you update a trip, you need to know which partition to go to update that trip, right? And so that's one of the most important one of the most important requirements, which goes into our next point, which is the bookkeeping for that data layout. You have to know where every single trip, which file it exists in and which date partition exists in, so that you can update it appropriately. Now, in order for us to do this, it really requires strong consistency. So we have to absolutely be right. We can't have corrupted data. We can't have the global index for where this data lives be inconsistent, which means that at some points in time you're writing to one date partition, another point you're writing to another, then we're going to have conflicting information. And so that was a very strong requirement for us. Also, you need to have high throughput. So the NoSQL store that you select for in this example has to be able to handle tens of thousands of QPS, essentially. Of course, it has to be horizontally scalable so that we can add nodes to the cluster and be able to scale our writes, and as well as our reads. And of course, when it came down to this and we took a look at this, we realized that this required a NoSQL store to support. So the two choices that we had were basically Cassandra versus HBase. And the decision that we ended up going with was to use HBase. So the reasons were, if you think about it from the perspective of the CAP theorem, we wanted to trade availability for consistency. So here we're talking about, like, let's say example HBase goes down. Now we may not have the latest data ingested into our Hadoop Data Lake, and so our data may not be the freshest, but we trade that off for consistency. We absolutely need the data in there to be correct so that we can run analytics on it. And so, so it's okay to be down for short periods of time. And in practice, the SLAs for uptime availability for HBase has been pretty good at Uber. And so periods of time it can go down, but we can catch up pretty quickly once it's back up. And then also, we have automatic rebalancing of HBase tables via region splitting. So as far as I know, I'm not a Cassandra expert, but this is not a feature available in Cassandra. But as you write more data into HBase, the regions can automatically split. And in certain cases, to load balance, we can move regions to new servers. So we can automatically scale out our reads, and as well as our writes. And so also the master-slave architecture, we have a global view of the spread of the data set across the cluster, so it helps us in determining data set specific throughputs, because each data set that we ingest through Uber, first of all, they have different priorities, and they also have different throughput requirements. So some of them have very low QPS, and other ones have incredibly high ones. So along those lines, that's why we ultimately ended up selecting HBase. And so now I wanted to talk about how the global index actually works. Now in this slide here, the green boxes are updates and the red boxes are inserts. And so what happens first is we process these inserts and updates. This is all run on Apache Spark. So we have a Apache Spark running on top of Hadoop, running our ingestion process. And so what we do for every single record is we query the global index. Is the record key found in this table? If it's not found, that means that it's an insert. So what that requires is that we insert that new record into HBase, so that next time if we do an update, we can find that insert. If it is found, then it is an update. So what we do is we know where that file, for that record, we know again what date partition it lives in and which row key it is and which file it is. So we can go in and essentially either overwrite the Parquet file, create a new one, or we write what we call, there's another process where we actually write an Avro file, which is row data, and then we compact that in the background. So those are two options that we have with Hoodie. So another view of this is just all the sources that we ingest from currently, Kafka, MySQL, Cassandra, Schemaless, goes into our global index. And then again, it writes to, for that Hive table, it writes to the files and the specific partitions. So in terms of generation of global indexes, I wanted to, again, highlight that the vast majority of the life cycle of ingestion is batch uploads. So if you look at batch 1 through n there, for every data source, we process the inserts, and then we insert the records into HBase. Now the QPS for this batch insertion is again probably in the thousands, which is well within the realms of what HBase can support. And then the one-time index upload, we have the Hive table, we derive the indices, we upload the indices to a key value store. Actually, it's not a Hive table, it's the source data store, which can be Kafka, MySQL, et cetera. And then we upload these indices to the key value store. So this is what I actually wanted to deep dive into, because we actually, if you think about it, again, we have to support millions of writes of QPS per second if we actually try to use the normal write path for HBase or any key value store. And if you actually go through the write-ahead log and then write to the mem table and then flush it to disk and compact it all in the background, that's it's actually relatively cheap for most cases, but if you're talking about millions of QPS, that's a very, very expensive process, and you're not going to be able to keep up. You're going to create hotspots. You're going to fall behind. The cluster might fail over. And so we realized that we couldn't do that. And so what we had to do is we needed to split the case for using a NoSQL store for batch versus incremental. So incremental, we're already pretty good. We can use the normal HBase write path or any write path for a NoSQL store and just write to memory, flush to disk, and it should be able to handle it pretty well. For the one-time index upload, that was a problem, and we had to design a new system to circumvent that normal write path. And so what we basically did, let me just talk about how this actually works, where we actually generated the H file ourselves and uploaded them into HBase. And so the way that we did that is we have something called a Bootstrap library, and we take the data store of truth, and we use Apache Spark, and we create a resilient distributed database dataset. For those of you that aren't familiar with Spark, it's called an RDD, and this is from the dataset will use the Bootstrap library to create these incremental backups of the dataset in HDFS as sequence files or some sort of binary encoded format. And we will read them through Apache Spark, and we will create, in the RDD, we will sort on the record row key and the column name. And so the entire RDD is globally sorted on this record row key. And then the entries that are shown in green here, this is how we identify for every single trip. Again, taking trips as an example, you'll know for this trip, it's located in this Hive partition, and within that Hive partition, it's located in this file name, and then it's located in this commit ID. Because again, using snapshot isolation for Hoodie, what we do is we write copies of the Parquet files with the update. So if your trip changed, we'll actually update the Parquet file, create a new one with the new trip information, while the old one still exists. And so people can query the old one while you're writing the new one. So it's just a standard Lambda architecture snapshot isolation use case there. And so from there, what we actually need to do is we need to now break it down from the top one to the record row key, sorted by the record row key and the column name. So there's 3 column names: commit ID, file name, and partition ID. And so we need to sort it based on that. Now, I'm going to talk a little bit about how that actually is done in Spark. So this is the DAG of the Spark execution model. I apologize that the text there is a little bit small. It's hard to get it all on the slide. But first, in stage 1, what we basically do is we read in all the data, and then what we do is we go to stage 2. via a shuffle of all the row keys. So we sort all the trips by row key. And so for those of you familiar with Spark, every time you do a shuffling of data, that is a new stage. And so now we have the row keys, all the trips sorted by row key. And what we need to do is we need to transform it from this top one here to the bottom one where you have the record row key and the column names. So now it's sorted by key value, by the key and the column within that partition. Now, what happens is when you do this transformation, you now have it sorted by the record and the column name, but the actual, within each partition, you actually lose the sorting of the row key, right? And so this is just, I think this is just a feature of Spark, unfortunately used as sorting. So what we need to do is within that partition, we do what we call a repartition and sort within partitions of that row key again. So now your data is again sorted within the row key, but it's now also sorted by the column names. And so the partitioning is unchanged here, and so that helps us actually not have to shuffle too much or shuffle data around. And so each partition actually corresponds to a non-overlapping key range for H files. And the reason why we do that, if you look at the H file upload process, when we read, if you have all these non-overlapping key ranges of partitions in Spark, we do that on purpose so that each partition corresponds to an individual H file that we create in the back end, right? And so the reason is that if you actually just didn't do that and you uploaded these H files into the back end, the upload latency will be really severely affected because you'll have to actually split the H files on the back end, and that's not good. And for the amount of data that we are trying to split, like some of our data sets are, again, tens of terabytes, it would take a long time to do that. I don't know exactly how long. I think estimates is like over a day, right? A couple days. And so what we do is every single partition corresponds to one region, one H file. And so when we actually upload it, we do not have to split the H file. And that allows us to be able to really reduce our upload latency. Actually, the uploading only takes about 10 minutes, even for tens of terabytes. It's the H file index generation that is the bulk of the time. And so I believe we are able to update, actually create these HBase index files in a couple hours using the Spark DAG that I just showed. So I hope that makes sense. That was a real key feature of what we tried to do, where each partition, again, is identified with one H file for one region, so that there's non-overlapping regions. We don't ever have to worry about updating everything. Everything we know is split and is non-overlapping again. So along those lines, we actually did even more tuning. I'm just going to go over this really quick, but again, for Apache Spark, we realized that some of our classes were not explicitly registered with cryo serialization. So this is just a really simple optimization. Within the Spark job, if you look at the actual data, you'll have the fully qualified class name if you don't explicitly register it with cryo serialization. So per record, it's a pretty small improvement, but if you think about it, over 54 billion indices or 54 billion records, not having to contain the entire fully qualified class name is actually a pretty big savings. We were able to reduce our job from 3 shuffle stages to 1. Now, again, shuffling is very expensive in Spark because you have to move data across the cluster and get all the data co-located so you can do the maps and the other functionality on top of that. We also had to tune our H file size and our partition counting size. Again, we had to make sure that each H file corresponded to one region, but within that, we had to tune that ourselves. And then I hope that we'll have an Uber engineering blog post on that soon. So from that perspective, we were actually able to take a 13 terabyte index data file with 54 billion indices and generate them within 2 hours and load them in 10 minutes. So that's a huge, really huge improvement. So yeah, it's really we're really happy to report that. In terms of throttling HBase access, each of these jobs, these Spark jobs, when we're running the ingestion process, has to query HBase for every single read and for every single write. And so what we did was, in the beginning, we had something called a QPS fraction. For every job, we can configure it to take a fraction of what we configured our HBase cluster for maximum reads and writes. And so we are currently almost in production. We have a process where we actually maintain stats across all ingestion runs, so we can see. One of the benefits of Hoodie is we have a lot of metadata about each data set, so we can see like every run, how many writes we had, how many updates we had, and how many inserts we had. And so we are able to dynamically change the way that our jobs work in terms of the HBase QPS throttling to give more for data sets that have increasing amounts of data. We can give them more QPS fraction to talk to HBase with, and the ones that have less, we can basically reduce it so that we maintain the optimal usage of our HBase cluster. So this is a graph just showing this. So we have this QPS throttling in place. And so when you actually add region servers in HBase, so this is one region server on the left, and you'll see we added it, we increased it to 5 HBase region servers, and you'll see the throughput that automatically increases with that. And so we don't have to, there's no SRE manual work involved here. It will automatically scale and increase when you add region servers. So in terms of next steps, we wanted to handle non-append only data during Bootstrap. So what I just described was we scoped the problem on purpose, and we made appropriate trade-offs to ensure that when we create these HBase index files, they don't have non-overlapping regions, so we can bulk upload them to HBase, right? And so at a certain point in time, we want to think about handling non-append only, and there's a lot of challenges in that. I don't know all of them to go into it, but we also wanted to explore other indexing solutions. We may not continue with HBase in the future. I think it actually is handling it pretty well, but we'll see as we continue to increase our ingestion throughput. We may want to switch over to something else. Here's some useful links. We have 2 open source projects, Marmory and Hoodie. Hoodie is our storage engine that we actually use to store the data in our Hive Data Lake. Again, these are essentially Parquet and Avro files with metadata around them to allow us to do like incremental reads and things like that. And then Marmory is our ingestion and dispersal framework that was also open source. I also have 3 engineering blogs on the right. One of them is about what this talk, the global indexing and data partitioning. The second one is about the Uber Big Data platform journey, how we actually started from having everything on one MySQL box to now having this huge data lake with over 100 petabytes of information of data. And then the last one is our ingestion and dispersal framework, Marmory, that we open source. So I also have another Dataworks Summit talk about our data ingestion dispersal framework tomorrow at 11. Be great to see you guys there. And then I also wanted to give proper attribution to some of the engineers on the team. So Kaushik, Nishit, and Jing were the engineers that primarily came up and wrote this framework, or this HBase global indexing solution. And then Jing was also the engineer that helped really to scale it, to get it to run in the 2 hours to create the indices and 10 minutes to upload. Last one is just a shameless plug. We are hiring Seattle, Palo Alto, San Francisco. I am an engineering manager. Please come talk to me. I'm happy to, yeah. So it is a great place to work. So there is an email address. So if you email Hadoop platform jobs with your resume, if you guys are shy. And yeah, thank you. Are there any questions? We have about 5 minutes. Yeah.
Curious in your app, if an index doesn't respond in time, or there's some other increased latency, how do you respond in the app?
Yeah, so that's a great question. So that's why we actually we made that trade-off where we wanted strong consistency versus availability. So if it takes a long time to respond, our jobs will run slower, but we will never sacrifice correctness. And we have had cases where we have seen that, or actually HBase has actually had to go down, went down, or we had to do a hard reset for other purposes that I don't want to get into. And so we actually had to pause our job. So we can actually pause our jobs. We have checkpoints in our data stores, so we know where we actually last ingested from. So if for whatever reason HBase has any issues, we can just restart the job. It's idempotent from that perspective, and we can restart the job from that last checkpoint. But usually what happens is the job just runs a little slower, which is generally okay, because the way that we tuned our jobs is that running our jobs for about a day will allow us to catch up on about 2 days worth of data. So the reason we do that is because when we do the Bootstrap, we have to pause. We have the incremental data still flowing usually into Kafka, and so that Bootstrap we try to finish within like 24 hours or something so that we can catch up. If it takes too long, then the Kafka retention policy will start dropping data and we'll actually lose it. So, yeah.
In the context of cell versus rows,
Yeah.
In the row we keep the latest state of the, say, the given trip, right?
Yeah.
And we keep updating until it's finished. So
Yeah.
once the trip is done, do you guys still keep that record in the row, or it gets moved to
Yeah.
cell and then maybe?
Oh no, we always maintain a cell and a row table. That always is in perpetuity. What happens is we actually have data around like how much data is accessed, the query patterns, and so we see that, like, for example, it makes sense, right? Like within a week of a trip, you might have a lot of analytics run on it, but after 6 months, you're not going to. But what happens is, what you would be surprised is there is a lot of updates to trips all the way from 2015, because we're constantly updating our data model and we may have to add new information. And so we'll actually rewrite all that data. So we need that HBase Global Index to still find that data. So we have to maintain like forever all the indexes and information, so we can never drop it. Yeah, the cell data is orders of magnitudes larger in terms of the number of rows, but it's much easier because it's append only. So it's a much cheaper to write to. Yeah. So generally we run it. Ideally, we would like to run it just once at the beginning of the life cycle. But what's happened is any sort of service interruptions, or if we lose data somewhere, we can always rebootstrap. We have a process to rebootstrap data to catch up on everything. There's been cases where, unfortunately, there's like data corruption, and we had to do things like that. Or yeah, so we have the ability to rebootstrap data, but ideally it should only happen once. Yeah. Was there a question? Yeah. How many resources in terms of Spark? Or I actually don't know off the top of my head, but I think it's in the thousands of executors. So we use Yarn at Uber, and we have a pretty large Yarn resource like allocation. Yeah. Yeah.
In the cell and row tables that you were talking about, like making those Hive partitions.
Yeah.
It seemed a little funny because architecturally that's very similar to how HBase is doing things under the hood, right? It's recompacting things. It can hold on to multiple versions of cells.
Yeah.
It can give you the latest view of the cell. Without getting into too many details about, you couldn't scale a NoSQL store up to handle that volume of data. Did you guys do experiments with it and found, like, was it like a cost decision? Like, I don't want to spend enough money to run an HBase cluster large enough to host that? Was it we don't have, like, the chops, we think, to run a cluster that large?
So millions of QPS per second being able to handle that would require a pretty large HBase cluster. And so we were able to so I hope this is answering your question, but we were trying to circumvent that by doing this. If you can just upload the H files on the back end, then you just solve that problem, and you don't have to all the resource requirements for HBase. Like the cluster size will be dramatically smaller. The amount of maintenance will be dramatically smaller. Yeah. So does that answer? Yeah.
Sort of.
Okay. I can talk more. Yeah. Yeah.
Like I've got a number of clusters that do millions of queries per second, millions of ingests per second. There tend to have clusters, tens of clusters.
Okay.
And so yeah, it's very interesting because the HBase book load, the HBase book load is always such a problem for my tenants who do that infrastructure very rapidly. And so did you find a number of kind of compaction and split tunes that were necessary for your
I may not fully understand that question. So actually, one thing I wanted to clarify was that the millions of QPS would probably be for the same date partition, which means that it would probably be for the same set of nodes when you're actually doing that writing. So it's not split, distributed across the cluster. So you have these hotspots that we also wanted to avoid. Yeah, I don't, in terms of like the compactions and all the other information about HBase, I don't actually fully know all those details of how we tune that specific part. A lot of our tuning was in terms of the Spark tuning to reduce again the shuffles and to make sure that we again split the partitions so that corresponded with H files, so we could just simply upload it and not split the files. I think in terms of HBase compactions, I don't think we actually ran into a lot of issues there. I could be wrong. I can ask our engineers, but I don't remember running into too many issues on that. Yeah. Cool. Any more? Yeah.
Did you mention you were creating partitions per update? Like, wouldn't it be a lot of files causing name node scaling problems?
Oh yeah. So we overwrite the Parquet files. So in terms of name node scaling issues, so yeah, we do have we can either, the Parquet files are tuned to be like the block size, which 512 megabytes or 1 gigabyte, I forget exactly which one it is. And so we are able to write at that level, and so it reduces the amount of files. But the other thing that we do is, if you're talking about our hoodie storage system, we actually have there's a copy on write where we overwrite the Parquet files, and there's a merge on read, which is hoodie 2.0, where we actually don't overwrite the Parquet files, because the problem is if you have a Parquet file and you only update one trip, you have to overwrite the entire Parquet file while updating that one trip, which means like the other millions of rows are all the same. It's very inefficient. So we have this new process where you actually write the changes as avro in rows, and we have a compaction process that will on the back end merge that into the Parquet file after a certain period of time. So it collects all the changes over a period of time, and it makes it much cheaper, if that makes sense. And also it can do it asynchronously. So we used to do it during the ingestion run. It actually overwrites the Parquet file. Now writing the changelog or avro changelogs are much cheaper. So we kind of, I mean, I'm getting into like some separate issues from HBase, but it kind of decouples that bottleneck. Does that make sense? I hope that makes sense. Yeah.
Something similar to write-ahead logs or...
Yeah, exactly. Yeah, it's kind of like emulating a key value store in by where you do a write-ahead log, but except the write-ahead log is avro in this case. Yeah, I think we're out of time, so I'm happy to talk more. Thank you.